So we've had some basic exposure to problem solving in electrostats, and let's say almost 3/4 of the ideas that are required towards problem solving, they've been taken care of in the class, giving us an opportunity to take on to more problem solving. Not that this is advanced problem solving, but for sure problem solving that will help us learn how to apply the ideas that we've already learned. Right? I'm also assuming that you've been practicing problems at home, so that the class eventually turns out to be meaningful for you. Right? So refer to the sheet titled Electrostatics Charging On. So the first problem is about an infinite sheet of charge with surface charge density sigma spread over it and a particle-like mass carrying a charge minus q, assume q to be positive, resting on a horizontal frictionless surface, say at the point A, at a distance L from this infinitely large sheet. We want to discuss the motion of the block, assuming that the collision of the block with the sheet is perfectly elastic. We will assume that, well, this is positive charge and this is negative charge. It's going to attract this particle to this. It will undergo a collision, and then there is going to be a perfectly elastic collision of this with the wall, let's say, and then the velocity will get just reversed. Right? There would be no loss of kinetic energy of this particle. The velocity will get reversed. We want to discuss at length the nature of the motion exhibited by this mass m. Right? Now, fairly simple problem. Realize that this mass m is under the influence of an electric field which is sigma by 2 epsilon naught to the left because of the infinite sheet of charge. Yes or no? Right? And therefore, this is going to get attracted towards the sheet. The force acting on this, F, is going to be given by the force would be rightward and would be the magnitude of the charge on this mass into the electric field, sigma by 2 epsilon naught. Yes or no? That's going to be the force on this mass. Clear? It's a constant force. It's a constant force, and therefore will result in a constant acceleration to the right. Therefore will result in a constant acceleration to the right. Yes or no? So the acceleration rightwards is going to be force by mass, which is q sigma by 2 epsilon naught m. That's going to be the rightward acceleration that this mass will have all the time. Right? For sure it cannot be SHM, because in SHM, acceleration will be proportional to displacement from a certain fixed point and would be directed towards a fixed point, and which is not the case. It's a constant acceleration, so it hardly qualifies to be simple harmonic motion. Right? Now, with this constant acceleration, it will traverse a distance L before it undergoes collision with B. Right? And the time taken is t0 seconds from A to B, given by L equal to half of A into t0 squared. Half of A into squared. T0 will be the time taken to go from A to B under the influence of an acceleration A to the right. Yes or no? So T0 is going to be root 2L divided by the acceleration, which is q sigma by 2 epsilon naught m. Yes or no? Right? 2L by acceleration, 2L by acceleration. That's going to be the time it takes to go from A to B. Clear? Now, by the time it reaches B, it would have developed a rightward velocity v naught, which is going to be what? At naught, which would be u plus at naught. So at naught, u is 0, right? And subsequent to the collision at B, its velocity will just get reversed. It will have a velocity v naught to the left. It will have a velocity v naught to the left. But its acceleration continues to be a to the right. While it moves with the velocity v naught to the left, it has an acceleration to the right, a. That's not going to change, isn't it? Because the force because of the electric field will continue to act to the right. This acceleration opposing the velocity will retard the velocity. Eventually, the particle will come back to A with 0 velocity and would execute the motion from A to B again and then from B to A again. Now, very clearly, one simple thing that happens here is the velocity time graph. From A to B, let's say, at t equal to 0, it's at A. It increases linearly in t naught seconds. It becomes v naught. The slope is positive because I'm taking rightward positive, so acceleration, which is the slope of the VT graph, is going to be positive, right? And then at an instant of time t naught, its velocity becomes negative. Same magnitude but negative. So then its velocity becomes, say, minus v naught because it's leftwards, but its acceleration is still positive. While it's moving to the left, its acceleration is still positive, so its velocity now again turns to 0 after a while. Its velocity again turns to 0 after a while. And very clearly, the slope of this will be the slope of this, representing the acceleration which is rightwards. And since these two triangles are identical, so if this is t naught units, this must also be t naught units. This is the time taken to go from A to B, and this will be the time taken to go from B back to A in t naught seconds. And this area is the same as this area. So displacement from here to here is the same as displacement from B back to a point where the velocity becomes 0. And therefore, it has to come back to A with 0 velocity. It has to come back to A with 0 velocity, and it takes t naught more seconds to come back to A, right? So then, from A to B and back to A, it has completed a full cycle of oscillation. But this oscillation is not simple harmonic motion. It's just an oscillation where the particle goes from A to B and back to A and then to B and then to A and so on and so forth. And the time it takes for a full oscillation is 2 t naught seconds. A to B and back to A is 2 t naught seconds is the time it takes. Motion is oscillatory but not SHM. Motion is oscillatory but not simple harmonic. Clear? Simple, right? How many of you got problem 1 right independently? Okay, quite a few of you. Very good. Right. In problem 2, we have a non-conducting, uniformly charged spherical shell. Non-conducting, uniformly charged spherical shell kept on a rough, non-conducting horizontal surface. Non-conducting but uniformly charged spherical shell. Mass of the shell is 2 kgs. Switch off your mobile. And the total amount of charge Q given to the shell is 1 coulomb. Oops, my phone. I didn't realize it's my phone that is springing into action again and again. Damn thing. Shut up. Q is 1 coulomb. And the friction coefficient between the surface and the shell is 0.18. Mu, coefficient of static friction, is 0.18. G of course is given to be 10 meters per second squared. We want to find the minimum value of the externally applied horizontal electric field uniform so that the shell starts sliding on the surface. That means the minimum value of E, so that this could slide on the surface, just about begins to slide on the surface, right? Now, let's very peacefully, calmly draw the free body diagram of the shell when subject to an electric field E. Now, since Q is uniformly distributed, right, when subject to an electric field E, then every element on the shell will experience, let's say dq is an element, charge element, dq will be dq into E, the force. So all the force elements would be rightwards, dq into E, dq into E, dq into E, and the total force acting on the shell would be the total charge on the shell into the electric field, and for all practical purposes we can look upon that as 1 acting the center, which is Q into E. Yes or no? That's a force acting on the spherical shell owing to the electric field E that is applied. Right? Now, there is friction acting. Let's say small f. This is static friction or kinetic? I mean, in the sense that if it just about no, what we'll do is we will find the maximum E so that it rolls. The maximum E that it rolls will be the minimum E that it is required to slide. You know what I'm saying? The maximum E. So if there is a limit to the value of E for which you can still expect it to roll, right? So that maximum E for which it could still roll is really the smallest E for which it begins to slide. Yes or no? Isn't it? So we are conceptually looking at the maximum E for which it still rolls on the surface. It begins to roll on the surface so that the conditions for rolling could be deployed. You know what I'm saying? So that's how we will look at it. Now, so then in that context, this F static friction would be less than or equal to mu mg, Now, under the influence of this, let's say it develops an acceleration a to the right. Let's say under the influence of these forces, the center of mass of the shell develops an acceleration a to the right. Now, time for us to write the equation of motion for translation as well as rotation for this shell, right? So, for translation, F minus small f is mass into acceleration. That's the equation for translation, right? Now, we can take torque about the center of mass and apply tau equal to I alpha. Torque about the center of mass and apply tau equal to I alpha. Torque about the center of mass would be F into, let's say, the radius of the shell, says R. So, it's a clockwise torque that acts on it. What's the clockwise torque acting on it about the center of mass? F into R is the clockwise torque acting on it, producing a clockwise angular acceleration alpha at the initial instant, right? So F into R is I. What is I? I about the center of mass for a spherical shell would be how much? 2/3 mr squared is 2/3 mr squared. So it's going to be 2/3 mr squared into alpha. Yes or no? Yes or no? Tau equal to I alpha applied about the center of mass of the shell, right? So then, now, condition for rolling without slipping. Yes or no? What is the condition for rolling without slipping? A equal to R alpha. In accelerated rolling, condition for rolling without slipping is A equal to R alpha. Acceleration of the center of mass would be the radius into angular acceleration. So this R alpha I can write as A, isn't it? A is R alpha. So what I do is right here, this R alpha I write as A. So this is 2/3 MA. So F is 2/3 MA, yes or no? Now, so capital F then is going to be what? MA plus 2/3 MA, which is 5/3 MA. MA, isn't it? Put small f as 2/3 MA, so capital F would be 5/3 MA, right? Now, capital F by small f is going to be what? 5/2, right? And capital F is 5f/2. Capital F therefore is 5f/2, but small f, since it's static friction, because we are assuming that it still rolls. We are assuming that it still rolls, right? So small f must be less than or equal to maximum static friction. If it is just rolling, then small f must be static friction less than or equal to maximum static friction. So this is less than or equal to 5/2 mu mg. Yes or no? F less than or equal to 5/2 mu mg. How about it? Right? But what is F? F is going to be Q into E. F is going to be Q into E. This F I write as Q into E less than or equal to 5/2 into mu, which is 0.18 into G, which is this. Yes or no? Q is given to be this. So E max will be this. Yes or no? 1.8, so 0.9. So how much does it turn out to be? 5.9, 4.5? 4.5 is it? E less than or equal to 1.8 by 2.9, 4.5. Yes or no? So E less than or equal to 4.5. Oh, mass, have I missed out mass? How much is the mass? 2 kgs. Okay, okay. So this makes it 9. 9. Mass is 2 kgs. So this is E less than or equal to 9. Yes or no? So that means maximum value of E for which it still rolls on the surface is 9 newtons. That means when E just about becomes 9 newtons, it's on the verge of sliding over the surface. That means E in excess of 9 units, 9 Newton per coulomb, E in excess of 9 newtons per coulomb will cause it to slide. Up to E equal to 9 Newton per coulomb, it will roll, but E just slightly over and above 9 Newton per coulomb, this will have a propensity to slide over the surface. So E maximum is 9 so that it could roll, E minimum so that it begins to slide is 9 Newton per coulomb. Clear? How many of you got right independently? Okay, 2/5 you took. Okay.
We said that it is not rolling, so the acceleration would be greater than, so we found the reverse. So the side was reverse.
Okay. So maximum minimum E is 9 Newton per coulomb so that it begins to slide. An uncharged sphere of radius r, conducting sphere of radius r, this is a conducting sphere of radius r, is at a distance small r from a point charge capital Q. This is the center, and there is a charge plus Q from which the center is at a distance small r. This distance is given to be small r. We want to be able to find the potential at the point P inside the sphere. There is a point P inside the sphere at a distance r1. At this point we want to find the potential. At this point we want to find the potential. Okay. Now see, if this is a conducting shell, right, E at every point inside the shell must be 0. Inside a conducting shell, inside a conducting cover, E at every point inside must be 0. That means this must be a region of 0 electric field and therefore constant potential, right? That means the potential at O must be equal to potential at P. Yes or no? Potential at O must be equal to potential at P. Now, so It will be easier to deal with the center of the shell than a point eccentric from the center. That is the point P. So let us attempt to find the potential at the center, because that in turn would be equal to potential at any P inside the shell. Right? Now, if there is a charge plus Q here, what would it do to the shell? It will induce charge. Say negative charge on the nearer surface and positive charge on the further surface. Yes or no? There will be charge distributed on this, right? With the objective of doing what? With the objective of producing zero electric field everywhere inside. But it was a neutral conductor. Therefore, the algebraic sum of these charges must have been 0, right? Now, potential at O is going to be because of two things. Potential because of plus Q plus the potential because of these induced charges plus the potential because of these induced charges. These are induced charges. Potential at O would be because of plus Q and because of these induced charges. Clear? Now, because of plus Q, it's simply going to be KQ by small r. Now, because of these induced charges, what you do is you take a charge element dq here. The potential at O because of this dq is going to be what? K times dq divided by capital R. The potential at O because of a charge element dq is going to be K dq by R. The total potential at O because of these induced charges is going to be sum of all of this. Right? K and R will wriggle out. That's the same for all the dq's that lie on the surface. Right? So K and R will giving you the sum of all the dq's. What's the sum of all the dq's on the surface? 0, 0. Sum of all the dq's is 0 because it was electrically neutral. So this is the potential at O because of the induced charges. This is potential at O because of the induced charges, which is 0. That means the total potential at O is going to be potential because of plus Q, which is KQ by small r. KQ by small r plus potential because of the induced charges, which is going to be 0. So that's the potential at O, both because of plus Q and the induced charges put together. So what's the potential at P? It's going to be the same. Potential at P is going to be KQ by small r, isn't it? So potential at P is going to be KQ by small r. Now, if I said small r. Now if I said, what's the potential at P because of the induced charges? What is the potential at P because of the induced charges? What would that be? Now, the total potential at P is potential at P because of induced charges plus potential at P because of plus Q. Yes or no? This is the total potential at P and we know this. This is KQ by small r. Now, potential at P because of the induced charges we need to compute. Plus potential at P because of plus Q would be how much? KQ by R minus R1. Yes or no? So potential at P because of the induced charges is going to be this minus this. However, the problem only asks you the total potential at P, which is this. But potential at P because of the induced charges is going to be this minus this. Are you all certain about everything that I have said so far? Yes or no? This would enable us compute the potential at P because of induced charges. Potential at P because of the induced charges will not be 0 because, see, reason being very simple. If I took a charge element here, say dq, and I look at its distance, say r prime, then the potential at P because of this induced charge is going to be k dq by r prime. The total potential at P is going to be sum of all of this. Now, realize that r prime is not a constant in this case because different dq's would be at different distances r prime from P. So, this r prime is incapable of wriggling out of the integral sign, and therefore you don't say that it's going to be k by r prime and sum of all the dq's, which is 0. It doesn't happen that way in this case, right? Potential at the center because of the induced charges is 0, but potential at P because of the induced charges is this minus this. Yes or no? Problem 4. We have a conductor in the form of a shell. This is the cavity. The inner radius of this is R1. The outer radius of this is R2. The center is O. And there is a point P. There is a point P at a distance, what, R2? It's given R2. R2, at which a charge plus q is kept. At this point, a charge plus q is kept. At a distance R2 from the center, a charge plus q is kept. Okay. Now, okay, don't call it P. There is a point P here. This point P is at a distance small r from the center. We want to find the potential at the point, we want to find the electric potential at P. We want to be able to find the electric potential at P. Now, there is a charge inside this cavity, plus q. What would it do on the cavity walls? Minus q. Will it be uniform or non-uniform? Non-uniform. If this q was at the center, then this would have been uniform. Now this q and this minus q will behave like a family, one unit, right? Now what would it leave? The outer surface with plus q. That would behave like a separate entity. Plus q on the outer surface. Plus q on the outer surface of the shell, right? Now, what would this plus q do? By itself, it will produce 0 electric field everywhere inside the spherical region, right? And therefore, what is the nature of distribution of this plus q on the outer surface? Uniform. Sigma inversely proportional to r. Since r is the same at every point, it will get uniformly distributed. For all points outside the shell, the effect, the electrical effect, is only because of this plus q on the outer shell surface. This plus q and minus q produce no electrical impact outside the cavity, be it in the meat of the conductor or be it outside the conductor, right? Those were facts that were unequivocally signaled to you last time, right? Okay. Now given this, we want to find the electric potential at P. The first part of the problem is we want to find the electric potential at P. Electric potential at P would be only because of this uniformly distributed plus q, and if plus q is uniformly distributed on a spherical surface, then for all points outside the surface, you can imagine this plus q to be concentrated at the center. So then the potential at P is going to be k times this plus q imagined to be at the center, divide this plus q imagined to be at the center, divided by small r. That's the potential at P. Yes or no? P. What is the electric potential of the conductor? We want to find the electric potential of the conductor, right? See, for points on or outside the shell, you can imagine this plus q to be at the center. If plus q is imagined to be at the center, then what would be the potential that this Q, when placed at the center, produces on the surface? KQ by R2. KQ, K times small q divided by R2. Yes or no? That's the potential here. And potential on the surface will be equal to the potential in the meat of the conductor. Because E0, the potential on the surface, if that's KQ by R2, then potential at every point of this meat is going to be KQ by R2. So the potential of the conductor would be its potential on the surface. Potential of the conductor is going to be its potential on the surface, which is KQ by R2. KQ by R2. How about it? Yes or no? Right? Clear, no? Find electric potential at O. Find the electric potential at O. Now, electric potential at O is what we want to find. See, there is a total amount of charge minus q distributed on this. It will produce a potential at O. That is, since all the charge elements, even though it's non-uniformly distributed, are at the same distance R2, right? This minus q, this entire bunch of minus q is at the same distance R2 from the center. Then this produces at the center, despite the non-uniform distribution, a potential equal to K times minus q divided by R1. Yes or no? See the shell, just the shell. This distribution on the cavity walls, this distribution on the cavity walls is minus q non-uniform, is minus q non-uniform because of this charge. See, if I took a charge element dq here, its potential at O, the center, is going to be kq, k dq divided by R1. The total potential at O, because of this minus q, is going to be sum of all of this, which is k by R1, and sum of all the dq's would be minus q here. Sum of all the dq's is going to be minus q. Let me call it d capital Q, because this. So sum of all the d capital Q's would be minus q. So k minus q divided by R1. So because of these charges on the cavity walls, the potential at O is k times minus q divided by R1. 1. Yes or no? Plus. Yes or no? Because of this plus q at O, how much will it be? kq by small r2. Because of this, kq by capital R2. Yes or no? This plus q alone on this produces zero electric field everywhere inside and produces a region of constant potential all by itself. The potential that it produces on the surface is kq by capital R2, and that's the potential it produces everywhere inside indiscriminately, right? So plus kq divided by k plus q divided by capital R2. That's the total potential at O. How many of you got it right independently? Which part? First part? All parts? C you missed out? No, you got right? Oh, very good. Find the electric field at P. Again, you know, will the cavity and its contents be instrumental in producing an electric field at P? No. So who would be? Charge on the outer surface. And if it's uniformly distributed on the outer surface, then for the spherical region, I can imagine this plus q to be concentrated at the center. Then the field that it produces at the center is going to be kq by r squared in this direction. Kq by r squared in this direction. That's going to be the electric field produced at P in the rightward direction. Yes or no? This plus q and induced charge on the cavity walls will produce how much electric field at P? Zero electric field. And this plus q and minus q in the meat of the conductor will produce how much electric field? Zero. Got me? Let me look at 5. So far so good, right? Fifth. there is a point O on a horizontal frictionless surface, and fixed point O, and a string is fastened to O. The length of the string is given to be, say, L, and there is a mass M. There is a mass M attached to this end A, containing charge Q over it. Particle of mass M with charge Q on it. And it's fixed to the point A, and the entire unit lies on a frictionless horizontal surface. Now, this is some line, and the position of the string is 60 degrees with respect to the line initially, right? The mass is initially at rest, the mass is given to be at rest initially, and is subject to a uniform electric field. Suddenly a electric field, uniform and horizontal, parallel to this, is switched on. There is an electric field in the rightward direction, parallel to this line, switched on. So obviously, no, the constraint is, this is a string, the particle will experience a rightward force, but its distance from O will not change, so the particle will execute a circular arc and will come to B after a while, The influence of circular motion, its motion has to be circular because of the constraints deployed, right? It will come to the point B. Now, what we seek to do is find the speed of the particle upon its arrival at B. Upon its arrival at B, the speed of the particle would have to be computed. Clear? Now, it's a simple case of work energy theorem, right? Realize that the particle is here. It experiences a force in this direction. Suppose I call it the x direction. It experiences a force in the x direction, which is Q into E. A constant force is what it experiences. Tension is a no work force in this case, because while it's executing circular motion, its velocity at all times will be along the tangent, whereas tension force would be radially inwards, right? And therefore, T dot V will be 0 from instant to instant. So T will have no participation in the work energy requirement, right? Will do no work, because at all points T and V will be perpendicular. V will be along the tangent to the arc, and T would be along the radius to the arc. They will be perpendicular to each other, so T will do no work. So the only force doing work is the force because of the electric field, which is constant and acting to the right. At all times, the force acting on the particle is to the right and is Q times E. Right? Now, work done by the force then. See, when it goes from A to B, what is the displacement along AB? CB. Yes or no? Its displacement along AB in the direction of the force is CB. Its displacement in the direction of QE is CB. Yes or no? When it goes from A to B. And CB, realize that this is L. So this is L cos 60 degrees. L cos 60 degrees, which is L by 2. And therefore, this CB will also be L by 2. Displacement in the direction of the force will be L by 2. So the work done by this force is going to be the constant force into the displacement in the direction of the force. So which is like QE into L by 2. That's the work done by the force. Now it starts from rest, means 0 velocity, and by the time it reaches here, let's say its speed is V. So work done by all forces put together is change in kinetic energy, which is half mv squared minus 0, right? So this is half mv squared minus 0. That's work energy theorem, classic work energy theorem. Work done by tension is 0. Clear? Are you all certain about whatever I have communicated? Right? There is this infinite sheet of charge with surface charge density sigma. Uniform sigma spread over it. So first of all, even before I proceed with the problem, just a few remarks. One, the field just outside this is going to be what? Sigma by 2 epsilon naught. Right? For small distances, this field will remain uniform and equal to sigma by 2 epsilon naught, right? Which means E varies only in this direction. E does not vary in this direction, right? If E is not varying in this direction, see, E is only like this, say Ex, which is sigma by 2 epsilon naught. Ey is 0. Ey is 0. Parallel to the sheet, the electric field is 0. So which means, if you transported a charge vertically, if a small positive charge was transported vertically, parallel to the sheet, what would be the work done? 0. Because Ex would be rightwards, whereas displacement would be upwards, so the work done by the electric field is going to be 0. That means, if you are moving it upwards, work done is 0. That means change in potentials is 0 in this direction. That means these points parallel to the sheet, these points parallel to the sheets are points at the same potential, right? So if there is a sheet, then uniform sigma, if there is a sheet with uniform sigma, then equipotential surfaces parallel to the sheet. Equipotential surfaces are surfaces parallel to the sheet, yes or no? Right? This would be one equipotential surface, this would be another equipotential surface, and so on and so forth. Yes or no? So, equipotential surfaces are set of parallel sheets, all points here are at the same potential, all points here are at another potential, and so on and so forth. Now, if these are two parallel sheets at a distance d, say, if these are two parallel sheets, not parallel sheets, parallel planes, if these are two parallel planes, parallel to the sheet of charge at a distance d, then which would be at a higher potential, this one or this one? Say this is plane 1 and this is plane 2. One will be at a higher potential or 2? Yes, because the direction of the electric field is from 1 to 2, and in the direction of the electric field, potential decreases. Yes or no? In the direction of the electric field, potential decreases. In this case, since the field is uniform, it will decrease at a uniform rate. Yes or no? So, if sigma by 2 epsilon naught is the field, when you go from 1 to 2, the total change in potential would be E into D. That will be the total change in potential when you go from plane 1 to plane 2. When you go from plane 1 to plane 2, the change in potential is going to be sigma by 2 epsilon naught into D. How many of you gather this? In a uniform electric field, if you go D units in the direction of the electric field, potential decreases by an amount E into D. Is that okay or not? Potential, that means potential at 1 minus potential at 2 is going to be sigma by 2 epsilon naught into D, where D is the distance parallel to E. D is the distance parallel to E. Yes or no? Clear? So, suppose this was an infinite sheet of charge. Suppose this was an infinite sheet of charge. And I go from P to Q like this. Say this is D, and say this is theta. Now I don't go from P to Q. What I mean is there are 2 points P and Q given. There are 2 points P and Q given like this. What is the potential difference between P and Q? Yes. What we would need is the electric field is in this direction, sigma by 2 epsilon naught. To the right, into the horizontal separation between P and Q. P lies on this plane, Q lies on this parallel plane. Right? All points on this plane, be it this P or be it this P, they will be at the same potential. All points on this plane would be at the same potential. So P and P prime would be at the same potential. So potential difference between P prime and Q will be the same as potential difference between P and Q. And what would be the potential difference between P and Q? The electric field sigma by 2 epsilon naught into D cos theta into d cos. Yes or no? Tell me. All's good? Now, let's look at the problem. There is a conducting sphere of radius r. Conducting sphere of radius r. There is this infinite sheet of charge. This distance is given to be 4r. And a charge plus q is placed near a uniformly charged conducting shell having surface charge density sigma. Charge plus q placed near a uniformly charged conducting, so plus q is placed here, let's say on this. Find the potential at A on the surface of the sphere due to charge on the sphere, Potential at A because of charge on the sphere. This angle is given to be theta naught, which is pi by 3, 60 degrees. Now, for sure, potential at A must be the same as potential at O. Total potential at A must be the same as total potential at O. Yes or no? Potential on the surface will be equal to potential inside, right? So the total potential at O, A, must be the same as total potential at O. Yes or no? Now, potential at A would be because of two things. Because of the charge plus q and because of the sheet, right? So potential at A is going to be potential at A because of the sheet plus potential at A because of plus q on the surface, because of plus q on this surface of the sphere, right? Potential at O is going to be because of the sheet, plus potential at O because of plus q. Yes or no? Now, between A and O, the potential because of the sheet alone, potential at A because of the sheet minus potential at O because of the sheet alone, like I said, potential at A because of the sheet minus potential at O because of the sheet is going to be what? Sigma by 2 epsilon naught into, this is R, and the horizontal separation between the two, which is R cos theta naught. So cos 60 degrees half. So sigma R by 4 epsilon naught. Right? Potential at O because of plus q is going to be kq by R. This is going to be kq by R. And this minus this is given to be sigma R by 4 epsilon naught. So if I take this minus this, then I'll have like a sigma r by 4 epsilon naught plus potential at A because of Q equals potential at O because of Q, which is KQ by R, right? So potential at A because of Q is going to be KQ by R minus sigma R by 4 epsilon naught. That's potential at A because of Q. A circular ring of radius R. This is a circular ring of radius R. Has charge Q uniformly distributed over it. Plus Q uniformly distributed over it. There is a sphere of radius R, same radius, having its center C on the periphery of this ring. There is a sphere which is, this is a ring of radius R, centered at O. Now there is a sphere which is constructed whose center lies on the periphery, and the sphere has the same radius as the ring. That's given, right? That sphere then would be like this. This is the sphere. This is the sphere of the same radius, having its center on the periphery of the ring, is constructed. We want to find the flux. We want to find the flux crossing the sphere of radius R. We want to find the flux crossing the sphere of radius R. That means we simply want to find the charge on this portion of the ring. Charge on this portion of the ring is the charge enclosed divided by epsilon naught. That's going to be the passage of flux through this sphere, right? So the problem is as simple as simply finding the charge on this arc, right? So simple. See, this is R, this is R, this is also R, right? This is an equilateral triangle, therefore. So this angle is 60 degrees, right? And this angle is also 60 degrees, right? Q is the total charge over 360 degrees. Over 360 degrees. Now, so this arc is like subtending 120 degrees at the center. So over 120 degrees, this would be the charge. Yes or no? So this divided by epsilon naught is the flux passing through this, right? The total charge therefore is going to be Q by 3 epsilon naught. That's the flux. Do you all understand this? This arc subtends an angle 120 degrees at the center. So which is 1/3 the total angle that the ring subtends. So the total charge on this portion would be 1/3, which is Q by 3 epsilon naught. That's going to be the flux passing through the sphere. Charge enclosed by epsilon naught. Clear? Is just about that from a spherical surface. Okay, I'll just come back to 7th. There is a portion which is the spherical cap subtending a polar angle alpha at the center, and a charge Q is placed at the center of the spherical shell. We want to find the flux over the remaining portion, which is what I just did. The total flux is going to be Q by epsilon naught minus the flux passing through this, which is like Q by 2 epsilon naught into 1 minus cos alpha, right? That's the flux passing through this remaining portion. Yes or no? I just discussed this with you a little while ago, which is like Q by 2 epsilon naught into 1 plus cos alpha, right? Which is Q by 2 epsilon naught into 2 cos square alpha by 2, which is Q by epsilon naught into cos square alpha by 2. Q by epsilon naught into cos square alpha by 2 is the flux passing through the remaining portion, right? So there are two particles, each containing charge Q. connected by a spring of force constant K, massless spring of force constant small k, placed over a smooth horizontal surface, and they are released when the separation between them is r and the spring is unstretched. That means the unstretched length of the spring is r. The unstretched length of the spring is r. That's given. Now, if the maximum extent, so what is going to happen is they will repel each other. They will repel each other, right? If the maximum extension of the spring is r, then the value of k is how much? If the maximum extension of the spring is r, that means eventually the charges will, because of repulsion, will acquire this position where this separation becomes 2r because the stretching is r, so the separation becomes 2r between the two charges. At this instant of time, what happens is, this is referred to as the maximum extension of the spring. This is referred to as the maximum extension of the spring. Now, we want to be able to find the value of the force constant K of the spring if the maximum extension of the spring produced is R. Simple problem. See, what is really happening here? Under each other's electrostatic repulsion, they move apart, the spring stretches, elongates. While the spring elongates, it tries to decelerate the charges Q and Q. The spring force on Q, this Q acts in this direction, on this Q in this direction. Yes or no? And therefore, the velocity of the two charges will decrease. Under the influence of the spring force, the velocity of the two charges will decrease. But the spring, as long as the velocity of the two charges is not zero, the spring will keep elongating. The spring will keep elongating. At some point of time, the charges would have got decelerated to such an extent that the velocity of the two charges become zero. So velocity of the two charges, and from symmetry it's going to be the same. Conservation of linear momentum, it's going to be the same. V0 at some instant. Now the spring will not elongate any further. So this then is the state of maximum elongation of the spring. Velocity of the two charges is zero. If it was non-zero, it would have stretched even further. If the velocity of the two charges was non-zero, it would have stretched even further. So in a state of maximum elongation, the velocity of the two charges will become zero. Clear? So then, between this state and this state, I can apply conservation principles, conservation of energy. The spring elongates by an amount r. So then, the gain in elastic potential energy of the spring is how much? Half k r squared is the gain in elastic potential energy of the spring, right? And it must have come at the expense of loss of electrostatic potential energy of the two charges, right? In this state, what is the electrostatic potential energy of the two charges? Kq squared by r is the electrostatic potential energy U1 of the two charges. In this state, the electrostatic potential energy Kq squared by 2r. So U has decreased. Loss in electrostatic potential energy accounts for gain in elastic potential energy. So half k r squared, where k is a spring constant, this capital K is 1 by 4 pi x epsilon naught, is U1 minus U2? Yes or no? Loss in electrostatic potential energy, which is kq squared by 2r. Yes or no? So half kr squared is kq squared by 2r. This gives you this value of small k. Yes or no? How many of you got it right? Okay. You also, yes? Huh? Well, yes. In the sense that, you know, you can imagine the whole thing. You can imagine as if, you know, these two charges are placed in an electric field, and there are external forces force F acting on this, there is a force F acting on this. In the center of mass frame, it will do that, right? So refer to my two body discussion, two particle oscillation that we did. So you will understand what exactly happens in the center of mass frame of this. Not in the ground frame, it will not do that in the ground frame. Huh? 2 point charges plus 2q and 8q are placed at a distance small r. Now we want to be able to place, so this is say point A, point B. And now there is a charge minus q to be placed between them, say at a point C, such that the electrical potential energy of the system is the least it could be. So that the electrical potential energy of the system is the least it could be. See, one thing that I must share with you on a very general note. Every system would like to acquire the lowest potential energy. It feels comfortable in states of lower potential energy. Every system, that's the propensity of all systems. They feel comfortable in lower states of potential energy. That's law of nature. That's law of nature. In the sense, do you find that, in fact, that's the way things are defined. When a particle falls down, it's actually the force, but we have defined potential energy that it decreases in the direction of the force then. So this then, the manner in which we have devised and designed our force fields, etc., and also potentials, in that context, it is easy to understand that, it's lower potential energy states that every particle would be in pursuit of. Isn't it? Because that's exactly the way we have defined potential energies. Particle falling down, etc. Moving in the direction of a positive charge, moving in the direction of an electric field, its potential energy decreases. So it's in pursuit, constant pursuit of lower and lower potential energies.
Low potential energy is like the field is in that direction, so the force is in that direction.
Yes. So it's about how we defined our potential energy, isn't it? Now, say we want to be able to locate a charge minus q between A and B at a point C, such that the system of charges is at its lowest potential energy state. Which means, say I place C at a distance x from this, and therefore at a distance r minus x from this. Now I will do no calculations on this. Please understand this conceptually, very easy. Suppose this was the state of lowest potential energy. Suppose this was the state of lowest potential energy for some value of x. And if you attempted to displace minus q slightly to the right, then it would aim at coming back to C. It would aim at coming back to C, because that's the state of lowest potential energy of the system. Yes or no? If you aim at displacing C slightly to the right, then it would want to come back to C one more time. That is its lower potential energy state compared to any other state. However, see, if I move it slightly towards B and let it go, at this point, let's say, and it's in equilibrium. It's an equilibrium at this point, right? That means, the attraction from this is equal to attraction from this, right? Now, if I displace it slightly to the right, what happens? The attraction from this increases, the attraction from this decreases. It has no desire to come back to C. It moves away from C. It moves away from C, right? And if it moves away from C, then C was not its destination ever. C was never a point which provided it solace in terms of lower potential energies, right? Which means the writing is on the wall. There cannot be a point C between A and B which will give the system the lowest potential energy. There is nothing like for the system a lowest potential energy. It doesn't have the lowest it's not like every function will have lowest and highest potential energies. If you don't understand this qualitatively, then you can do one donkey's job also, which books will do. Okay, books will do the following for this problem. I'll tell you what books will do, and that is, they will say, let's say at a distance x I place the system to achieve the lowest potential energy of the system. And then they'll say u as a function of x, total potential energy of the system as a function of x. 2q into minus q, k times 2q into minus q divided by x for this pair. Then for this pair, minus q into 8q, so k into minus q into 8q divided by r minus x plus, then for this pair, capital K, 2q into 8q divided by r. They will do this. Okay, potential energy as a function of x. And then they'll say, all right, if u has to be u minimum, if u is u minimum, you can do all of this, but it's all nonsense. Okay, if u is u minimum, du dx must be 0. Du dx must be 0. Right? They differentiate this with respect to x and put it equal to 0. And then they say, all right, here we come with a value of x. When you solve this equation du dx equal to 0, you arrive at a value of x. And then once you arrive at a value of x, you say, how do I, now this x for which du dx becomes 0 will either give you minimum potential energy or maximum potential energy. So now in mathematics down the line you will learn, if u is u minimum, then this is a necessary condition, and then a sufficient condition is d2u dx2 must be greater than 0. They say, all right, let me find the second derivative of u with respect to x and plug in x equal to that. If this will turn out to be greater than 0, then for that value of x, u is u minimum. And then they'll find, well, d2u dx2 doesn't turn out to be greater than 0. And therefore they will say, there cannot be a minimum potential energy. After all this nonsense, they'll come to this conclusion. But it doesn't require all that. In fact, let me make a statement and think about it. In a very general sense, let me tell you that a charge q, I will also explain this. A charge q placed in the electric field of several other charges. A charge q placed in the electric field of several other charges can never be in a state of stable equilibrium. Can never be in a state of stable equilibrium. Stable equilibrium, I have not yet discussed all of that, but stable equilibrium is equilibrium that represents lowest potential energy. Because when you move the particle slightly from its position of stable equilibrium, it comes back to its position, right? Because it's desirous of that position, right? In general, in electric fields, a charged particle in an electric field can never be in a state of stable equilibrium. Can never be in a state of stable equilibrium. We'll come back to that in greater details, but for the time being, do you understand the qualitative argument why there cannot be a human for this set of particles, right? And why doing all this is all nonsense, right? Shall we? Okay. So there is no minimum potential energy for the system. There is no minimum potential energy for this system. All right, let's look at, so option none of these, 10, option none of these. All right. There is a small sphere placed at a point A, which is u comma v, so that at the point B, So it's charged uniformly. That means for all points outside this, you can imagine the charge q to be at the center. Charged uniformly, so that at the point B, which is 8, 7, the electric field at B is given by the vector. Electric field at B is given by the vector 54 I cap plus 72 j cap Newton per Coulomb. Right? That's the electric field at B. And the potential at B is given to be plus 900 volts. 1. We want to find the magnitude of the charge Q. Number 2, coordinates of A. Okay, let me find these two, then we'll look at the last part. So one thing, the magnitude of the electric field at B is going to be what? Suppose separation between A and B is R. Then the magnitude of the electric field at B is going to be what? KQ by R squared. KQ by R squared would be the magnitude of the electric field at B, yes or no? Right? And that's going to be magnitude of EB, which is root 54 squared plus 72 squared. So 9 squared if I take common, so 9 into 6 squared plus 10 squared, which is 10. 90 Newton per Coulomb. Yes or no? See, if you took 9 squared common, 6 squared plus 8 squared, which is 10 squared. 6 squared plus 8 squared, which is 10 squared. So 90 Newton per Coulomb is the magnitude of the electric field. So this is 90. The potential at B is KQ by R, which is given to be 900 volts. Yes or no? Now if I divide this by this, I get R equal to 10. Yes or no? Do I get R equal to 10 when I divide this by this? Is it all given in these coordinates in meters or centimeters? Let me just check. All in SI units, right? Okay, I will assume SI. They have not given AB in 87 meters, centimeters. I will all assume it's all in meters. So there is no discrepancy on units. So R is 10 meters, separation between them. Now if R is 10 meters, you can solve for Q. You can solve for Q from this. Put R equal to 10 and you can obtain Q. Right? That's not an issue. Put R equal to 10 and obtain the value of Q, the charge on this. Now, how do I find UV? See, what is this vector? From A to B, 8 minus U I cap plus 7 minus V j cap. How many of you will want to believe this? The vector AB is position vector of this point, which is 8 I cap plus 7 j cap. Right? That's a position vector of this point. The position vector of this point A is going to be U I cap plus V j cap. Right? Final position minus initial position would be the vector AB. Yes or no? The vector AB is 8 minus U I cap plus 7 minus V j cap. Yes or no? And the length of AB we have found is 10 units. Now, do you realize that EB will also be in this direction? EB will be parallel to AB. Isn't it? Field because of Q at this point would also be along AB. Right? which means the direction of EB parallel to AB means a unit vector along AB will be a unit vector along EB. Would be a unit vector along EB, yes or no? Right? And what's a unit vector along AB? Unit vector along AB is AB, the vector AB, which is 8 minus U I cap plus 7 minus V j cap divided by 10. That's 10 is the length of AB. R turns out to be 10. So that's a unit vector along AB. A unit vector along EB is EB divided by the magnitude of EB. Magnitude of EB is 90. That's a unit vector along EB. Yes or no? Fine? So this is 9, which is 6I cap plus 8J cap. So it gives me 8 minus U equal to 6. Isn't it? Equating the XY components, U therefore is 2. And 7 minus V is 8, giving me V equal to minus 1. So 2 comma minus 1. Is that all right? How many of you got this right? Okay. Almost all of you. Okay. Very nice. Now, if the dielectric strength of air, E, which is dielectric strength of air, is 3 into 10 to power 8 volts per meter. Find the minimum radius of the sphere. Now, just get this right. Now, air in general is non-conducting. Air in general is non-conducting, right? But when you expose it to an electric field, it remains non-conducting for a while. It remains non-conducting for a while. If you go on increasing its exposure to the electric field, higher and higher values of the electric field, then what really happens is the air molecules get ionized. Air molecules will get ionized. There is charge separation. The charges separate significantly and they cause the medium to become conducting. They cause the medium to become conducting. And when a non-conducting medium becomes conducting, we say that the medium has got punctured. The medium has got electrically punctured, right? So there is only a certain value of an electric field which a medium can withstand, and up to which it will maintain its non-conducting character. But beyond that exposure, it will give in, it will cave in, and it will start to become conducting. So the minimum value of the electric for which a non-conducting medium exhibits conducting traits is called the dielectric strength. Is called the dielectric strength of the medium. So you don't expose a non-conducting medium to values of electric field higher than its dielectric strength so as to preserve its non-conducting character. Right? As long as you are not exposing a non-conducting medium to values of electric field higher than its dielectric strength, the medium will maintain its non-conducting traits, right? So there is a threshold value of the electric field which is a property of the medium within which the medium will continue to its original character. Any field in excess of that will cause the medium to get punctured, will start become conducting. So if there is a charge spread over this, right, then there is an electric field produced, and if that electric field is higher than the electric field, because of this charge just outside the sphere, is higher than the dielectric strength, then the surrounding air will get ionized, it will become conducting. When it becomes conducting, then the charge that has deposited over this will be carried away by the medium, because the medium has become conducting. This sphere will lose charge to the surrounding medium. Got me? So now, say if the radius of the sphere is r, and EB is a property that represents, let's say EB is the dielectric strength of this medium. Now, where is it that the medium is the weakest? Can I remove all of this clutter from here? Right? Sorry? Okay, 3 into 10 past 6. All right. Now, see, what really happens is if this is the sphere and there is charge Q, then for points on or outside, the electric field is going to be kq by r squared. For points on or outside the sphere, the electric field is going to be kq by r squared, right? You can imagine this q to be at the center. Now, as you keep moving further and further away, the electric field decreases, right? So it becomes less and less vulnerable towards a breakdown, towards a puncture, towards a dielectric breakdown. Dielectric breakdown is when it loses its non-conducting character, its insulating character, right? So then, so moving further away reduces the prospect of a dielectric breakdown. So then, if you from the surface, if you move further and further away, which is the most vulnerable portion? Just outside the sphere. Just outside the sphere, the electric field will be the greatest, and then it will decrease as 1 by r squared, right? So at this point, the maximum electric field occurs, which is kq by, let's say, the radius of the sphere squared. And if at this point it does not exceed EB, then at no other point will it exceed EB, because at this point it has the highest electric field, and this itself is less than the dielectric strength of air. So at no other point will it exceed EB, and there is going to be all safe play going on here, right? Right? So then, if kq we have already found, right? From one of the equations, kq is known. Kq by r is what? 900. So, isn't it? So kq is 900 into r, which is 9,000. So this is 9,000, right? So very clearly, r must be greater than or equal to root kq by EB to prevent dielectric breakdown. Root kq by EB. So this is r min. This is r min, for which there would be no dielectric breakdown. There would be no puncture of the medium. Right? This is the minimum value of r. This is the minimum value of the radius of the sphere, for which there is going to be no breakdown of the medium. Got me? All's good? Two very long wires are placed on a smooth horizontal table. Wires have equal but opposite charges, linear charge density lambda. So let's say this is minus lambda on this, minus lambda, charge per unit length on this, and this is plus lambda. And the initial separation between them is A. We want to calculate the work done by an external agent. Work done by an external agent per unit length of the wires, per unit length of the wire, to increase the separation from A to 2A, from A to 2A. Obviously, we will assume that no kinetic energy is added to the wires. So, let's say I apply a force on this. Then this force, in order that it could move it without adding kinetic energy, must balance the attraction between these two wires per unit. F is the force per unit length. F is the force per unit length. That must balance the force per unit length of attraction between these two wires. Yes or no? If this is minus lambda and this is plus lambda, then realize that the field here is, because of this wire, the field on this is minus lambda by 2 pi epsilon naught. Let's say a separation is x at some instant of time, the separation is x, minus lambda by 2 pi epsilon naught x to the right, which means it's as if lambda by 2 pi epsilon naught x to the left. Yes or no? That's the electric field to which this is exposed, right? Now if I just look at 1 unit length of this, then it experiences, let me just look at 1 unit length of this. Then what is the charge over this? Lambda is the charge over 1 unit length of this. So then the force that this 1 unit length of the wire experiences is going to be charge on this length into the electric field. So that's the leftward electrical force that this experiences, attraction between these two. The external, that is force per unit length, because I am now just talking of work done per unit length, so I will take force per unit length. So then the external force F, in order that it just about very slowly moves this to the right, must balance this so that no kinetic energy gets added. So the force applied per unit length, must be lambda squared by 2 pi epsilon naught x. The work done by this force to increase the separation by an amount dx is F into dx. That's the work done by this external force to increase the separation by an additional amount dx. right, which is lambda squared by 2 pi epsilon x dx, right? The total work done would be sum of all of this, where x runs from a to 2a, where x runs from a to 2a. That's the work done, which is like lambda squared by 2 pi epsilon naught log 2. 1 by x is log x, so log 2a by a, which is log 2. Yes or no? That's the work done per unit length of the wire to increase the separation from a to 2a. A charge q is placed on the surface of a sphere of radius r. We will assume that this is uniformly distributed. If nothing is given, we'll assume that this is uniformly distributed on the surface of a sphere of radius r. Now, because of mutual repulsion on the charged surface, the radius increases to a larger value, r prime. Larger value, r prime. Radius increases to larger value, r prime. And of course, now charge distributed over r prime on the surface. If the atmospheric pressure is P atm, show that the charge q must be this. See, while it goes from this state to this state, what happens to its self energy? Self energy is kq squared by 2r. Remember that? If r increases, self energy decreases. Yes or no? Self energy has decreased. Yes or no? What is the decrease in self energy? Kq squared by 2, 1 by r minus 1 by r prime is the decrease in self energy. This is the decrease in self energy. Now this decrease in self energy does not manifest itself as kinetic energy of the system. So it must have gone somewhere, isn't it? This must have been work done against atmosphere. Work done against atmosphere, constant atmospheric pressure, P atmosphere into change of volume. P atmosphere into change of PdV. Yes or no? So this must have assigned itself towards 4/3 pi r prime cubed minus r cubed. Work done against atmosphere. Pressure into change in volume. That's the work done against atmosphere. So decrease in self energy is work done against atmosphere. This is where, right? It consumed its self energy to so that it could push against atmosphere. Self energy decrease. Thermodynamics, remember this? If this was a volume, and if the volume, if this bulged out by a certain amount against a pressure, against a certain pressure P, then what was the work done? Pressure into change of volume, isn't it? Remember, it's the same thing. Pressure into change of volume, that was the work done, right? So pressure into change of volume is the work done. Clear kya? What? Correct? Okay, so you can obtain the value of Q from here, plugging in K equal to 1 by 4 pi epsilon naught, etc. Decrease in self energy manifests itself to push against the atmosphere, which is work done against atmosphere, which is atmospheric to change of volume. Look at those work calculations that we did in thermodynamics. It's the same thing. PdV, right? Work done PdV. See, next we have a solid non-conducting hemisphere. This is a solid non-conducting hemisphere of radius r. Solid non-conducting hemisphere of radius r has charge per unit volume uniformly distributed inside it. There is volume uniformly distributed, continuous distribution of volume rho, which is charge q, total amount of charge q divided by 4/3 pi r cube, 2/3 hemisphere, so q by 2/3 pi r cube, right? Now, dielectric constant of the material of the hemisphere. So 1 by 4 pi epsilon naught we'll use. K is given to be 1. A negatively charged particle having charge q is transferred from its center of its base to infinity. So there is a charge q which is transferred from O to infinity. We want to find the work done by the external agent in the process. Change in potential energy. Change in potential energy must be the work done. Yes or no? So, all the potential energy at infinity I will consider as 0. So, potential energy at O is going to be what? Potential energy at O is going to be Q into potential at O. Q into potential at O would be the potential energy of the charge at O. Charge q into potential at O, this is potential at O. This will give me the potential energy at O. This will give me the potential energy at O, yes or no? So all that I need to do is for this volume distribution of charge, right? For this volume distribution of charge, I want to be able to compute the potential at O. If charge is distributed in a hemispherical volume uniformly, if charge is distributed in a hemispherical volume uniformly, let's say a charge capital Q with volume charge density rho everywhere, what would be the potential at O? V naught. I want to be able to compute the potential at O because of this distribution. Is that right? Now, many ways you could do this, but essentially, you know, as you mature, it is about being able to identify elements effectively. Obviously, you know, for every charge element on this, you would compute the potential at O and you would sum it up, right? You can make life simple for yourself, you can make life complicated depending on your choice of those elements, how you've chosen those elements. I suggest that we break this entire volume. We break this entire volume into stacked shells like this. Shell. This entire thing could be broken down into stacked shells, radius x, where x runs from 0 to capital R. This hemispherical shell. If x runs from 0 to capital R, then I'll have stacked hemispherical shells creating this distribution, yes or no? X runs from 0 to capital R, I end up creating these stacked hemispherical shells which will produce this region, right? So this is a shell of radius x and of thickness dx. This is a shell of radius x and of thickness dx. Now, all the charge elements on this surface are at the same distance x from O, isn't it? This is like a spherical cap, a spherical hemispherical cap, a complete, right? And all points on this surface are at a distance x from O, yes or no? What is the surface area of this? 2 pi x squared. What's the volume of this into thickness dx? 2 pi x squared is the surface into thickness, because right, there is volume in this solid region. So 2 pi x squared into thickness. That will give me the volume of this region, volume of the shaded region, yes or no? Surface area into thickness. The total charge on this would be this, right? The potential, since all charge elements are at the same distance x from this charge distribution, then the potential at O is going to be k times the total charge on this divided by the radius x of this. Yes or no? Nahin? Do you all understand this? And therefore, so that's the potential at O because of this chosen shell. The total potential at O would be what? Sum of all of this, which is where x runs from 0 to capital R. That's the total potential at O. Right. 2 pi k rho, etc. will all wriggle out. Integrate x, so x square by 2, so r square by 2. Yes or no? That's the potential at O. Potential energy at O is going to be QV naught. Potential energy at infinity is going to be 0. Dielectric constant is like, see, generalized Coulomb's law, when I said that K, that's a dielectric constant, right? Departure from air medium, yes. Clear? Okay, did I tell you in any earlier session that if E is a function of x, then volume charge density as a function of x, epsilon naught dE dx kind of a thing? Have I told you that result? So we have a medium k equal to 1, where volume charge density is a function of y. If volume charge density varies with y, electric field varies with y. Electric field will be a function of y, right? We'll deal with that later on. Let's understand the problem first. A particle of mass m, having positive charge q, placed in the medium at a point A, which is 0 comma y naught. This point is A, which is 0 comma y naught, is projected with a velocity v naught to the right. Initial velocity is v naught I cap. V naught I cap is its initial velocity. Neglect gravity and frictional resistance of the medium and assume the electric field strength to be 0 at y equal to 0. E at y equal to 0 is 0. E at y equal to 0 is 0. We want to calculate the slope of this trajectory as a function of y. That means, you know, it will take up some trajectory of this kind. It will take up some trajectory of this kind, and at any given p, say x comma y, I want to find the slope of the trajectory, that is dy dx. Slope of the trajectory at any x comma y is given by dy dx, which is the slope of the tangent at that point. Slope of the tangent at that point is what it really means. Do you understand the problem? Now, so the particle is moving under the influence of an electric field because of volume charge density somewhere, right? So it is important for us to first identify the electric field exposure. So let me first find the electric field exposure. Rho is AY, that is epsilon naught dE dy, E will be a function of y then. If rho is a function of y, E will be a function of y epsilon naught. Did I tell you this result? Right? So Ay is this, dE dy. Therefore, dE is Ay dy by epsilon naught. Isn't it? dE is Ay dy by epsilon naught. Let me integrate both sides. When y is 0, E is 0. That's given. When y is 0, E is given. That's given. Yes or no? So when y is 0, E is 0. Then when y is y, E will be E. This will be E as a function of y, E at y. Yes or no? I'm sorry. At y, E will be EY. At y, E will be EY. E at y, right? So now when I integrate this, E at y turns out to be Ay squared by 2 epsilon naught. That's electric field as a function of y. Clear? That means when the particle is at y, charge q, it will experience a force q into E at y. That's the vertical force that it experiences. Now, what is the horizontal force? 0. There is no component of the electric field in the horizontal direction. Now, if there is no horizontal electric field, there are no horizontal forces acting on the particle. So what happens to its horizontal velocity? Remains constant. So the horizontal velocity of the particle, the horizontal velocity will remain V0 all the time. Whereas the vertical velocity will go on increasing, because electric field is going on increasing in the y direction. So force in the y direction will continue to increase. So acceleration in the y direction will increase, and therefore the velocity in the y direction will increase. And since the velocity in the y direction is continuously increasing, whereas the x component of the velocity is remaining constant, the graph is becoming more and more vertical, because the vertical velocities are continuously increasing. That is why this is the trajectory. See, the trajectory is becoming more and more vertical. The trajectory is really becoming more and more vertical, right? Now, at p, x comma y, Vy is the vertical velocity, right? Mass into acceleration in the y direction would be force in the y direction. Mass into acceleration in the y direction would be force in the y direction. What is force in the y direction? Q into E at y. Q into E at y is the force in the y direction. So Q into Ay squared by 2 epsilon naught. Q into Ay squared by 2 epsilon naught. Right? So this yes or no? Now, see, if I knew Vy, see, the net velocity would be like this. This would be the net velocity of the particle. Yes or no? Resultant of Vy and will be the net velocity of the particle, and the velocity vector will always be along the tangent, isn't it? The net velocity vector will always be along the tangent, right? So the angle that the velocity vector, net velocity vector at p makes with the positive direction of the x-axis, right? This tan theta will give me the slope at x comma y. This tan theta, which is the direction of the velocity, theta is the direction of the velocity, will also be the direction of the tangent, because velocities are always along the tangential direction. So tan theta would be the slope of the trajectory at x comma y, where theta is the angle that the velocity vector makes with the positive direction of x. So tan theta is all that we need to compute. Yes or no? So this is theta, the horizontal direction. So theta would be Vy by V naught. Tan theta would be Vy by V naught. So now I have to deal with Vy. I have to now deal with Vy. Right? Vy as a function of y. If I can find Vy as a function of y, good enough for me. Right? Now this I can write as Vy dVy dy. Yes or no? Tell me. Do you realize what I have done here? Dvy dt, those of you who are still dvy dt can be written as dvy dy into dy dt. But dy dt is vy. dy dt is vy. Yes or no? So dvy dt is vy dvy dy. vy dvy dy. And that must be qay squared by 2 epsilon naught m. This is dvy dy. Yes or no? vy dvy is qay squared by 2 epsilon naught m. Now this will give me access to vy as a function of y, right? Integrate both sides. When y was y naught, this is the point it started, when y was y naught, dy, dy. When y was y naught, what was vy? 0. When y was y naught, vy was 0. It started with the horizontal velocity, vy was 0. When y became y, let's say vy became vy. So this will give me vy as a function of y, vertical velocity as a function of y. So then vy squared by 2 is the left hand side when I integrate this, and the right hand side, this is y cube by 3. This is y cube by 3. So this gives me qa by 6 epsilon naught m into y cube minus y naught cube. Yes or no? This 2 will take care of this. This will be 3. So I know vy as a function of y. vy as a function of y is square root of this. Clear? What would my tan theta be? Tan theta would be the slope at x comma y. The direction of the velocity would also be the direction of the curve, that is the direction of the tangent at that point. So tan theta would be vy by v naught. vy obtained from here by v naught, that will give me the slope at any x comma y. That will give me the slope at any x comma